Alright, 46th lecture, elementary RLC one port synthesis and introduction to two port synthesis. This is the topic. As I told you in the last class, RLC one port in general poses a difficult problem, and if at all solvable, it is solvable by using a transformer. If the use of a transformer is allowed, then there is no problem, or you use a non-canonic synthesis of Bott and Duffin or some of its modifications. But as I said, in some special cases, if you are lucky, it is possible to synthesize an RLC impedance function, and we shall take a few examples to check the tricks of the trade. If these tricks work, perfectly all right. If they don't work, then they don't work. That's it. Okay. One of the examples that I take first is s squared plus 2s plus 2 divided by s squared plus s plus 1. You see that the poles, if this is an impedance function, you see that the poles are neither on the imaginary axis nor on the real axis. They are complex, and therefore, if at all realizable, it should be realizable as RLC. But before you check the RLC, you must check the realizability condition. There is only one in this case, because there are no poles on the j omega axis. That is a1 b1, which is 2 into 1, and square root a0 is square root 2 minus square root b0 square root 1 square. This is 2 and this is 2. So, with greater than equal to, it is equal to. Therefore, the real part condition is satisfied. You understand the shortcut procedure, because by inspection we see all coefficients are real and positive. There are no poles on the j omega axis. So, all that you have to do is to check whether a1 b1 is greater than equal to square root a0 minus square root b0. Greater than or equal to, it can be equal to. How come? What did I say? Where did I make it? 0.16. 2 into 1 and square. Oh yes, I beg your correct. Root 2 minus root 1 is 0.414 square. So it is greater than it. Okay. I am sorry I made that obvious mistake. But you see, if you make a continued fraction expansion, let us see if it works. S square plus s plus 1 blindly. I mean, I don't know how else I could do it. So we try continued fraction. S squared plus 2s plus 2. 1, this is an impedance, s square plus s plus 1. So, I am left with s plus 1 divides s squared plus s plus 1 s squared plus s 1 s plus 1. Let us see, this is admittance, then s 1 1 1 1 0. This is impedance and this is admittance. So, it does work. We have got all quotients which have real and positive coefficients, and therefore I can draw the network as 1 ohm, then an admittance of S, so 1 farad, then an impedance S, that means a inductor of value 1 Henry, and then an admittance 1, that is this. So obviously it is an RLC network, and that is why it was neither it did not satisfy the conditions of RC, RL or LC. But suppose we do it the other way round, that is starting with the lowest powers, alright. 1 plus s squared, 2 plus 2s plus s squared, 2, so 2 plus 2s plus 2s squared and minus s squared, we cannot go further. Suppose we do it the other way around, that is admittance. We take the admittance. Let us see what happens. Again lowest powers. Okay. So 2 plus 2s plus s squared divides 1 plus s squared half. So 1 plus s squared by 2, we are left with s squared by 2, this is an admittance, divides 2 plus 2s plus s squared, well 4 by s squared. We don't know how to realize this. Isn't that right? So we don't proceed further. Similarly, you can try other procedures and see if any of them works. You will have to try this. There is no established procedure to do this. We take another rather tricky problem. But you are sure that if one synthesis exists, there are other indefinite number. So maybe something else will succeed. All right. Now this problem is slightly tricky. S plus 2, S plus 3, S plus 1, S plus 4. Suppose this is given as an admittance, y of s. Now the poles and zeros do not alternate. First critical frequency is a pole, but then you have a 0, another 0, adjacent 0, then a pole. First is a pole, last is also a pole. So it cannot be RC or RL. It is not LC at all. But let us see whether it is positive real or not. S squared plus 5s plus 6, s squared plus 5s plus 4. A1 B1 is 25. A0 square root A0 minus square root B0 minus 2 whole squared. How much is this? Approximately 2.4. So obviously greater than sign is satisfied. Okay. So it is pure. There is nothing obvious in this which can make it non-pure. Therefore, we proceed by, let us say, start with partial fraction y of s. Well, in partial fraction you take the infinite frequency value is 1 plus, let us say, k1 divided by s plus 1 plus k2 divided by s plus 4. Let us try. Does this work? K1 multiply by s plus 1 and put s equal to minus 1, you get 2 by 3. That is positive. Good. 2 by 3. Then K2 minus 2 by 3. So this does not work. If it is negative, obviously we don't know how to do it. Okay. So we give up. We try y of s by s. Perhaps that might work. Let us see. S plus 2, s plus 3 divided by s plus 1, s plus 4, s. So it is k0 by s, 6 by 4, 3 by 2 s plus, all right, plus k1 by s plus 1 plus k2 by s plus 4. What about k1? S plus 2, S plus
minus 3, 2 by 3.
It's minus?
Minus 2 by 3. Minus 2 by 3.
Okay, doesn't work. Similarly, you can try the reciprocal of this, z of s. In either case, you see, if z of s works, then we know how to find. But z of s also doesn't work. One of the residues comes negative. Will z of s by s work? Because if it is ZRL, if it is RL, then you know z of s by s shall work. It doesn't work there either. I give up. I would not repeat this procedure. But then we ask, if it doesn't work, what is it that we are missing? And the clue is that tricks of the trade. There are no set patterns. The clue is the following. Let me show you this one. Yeah.
Can't we do this like continued partial fraction?
That also we'll try. We'll try. But let's exhaust my partial fraction. The clue is here. You see, K1 is positive, but K2 is negative. Now, is it possible to combine a part of this Is it possible to combine a part of this constant with this term which has a negative residue to make it positive? That's the clue. Well, if this was not there, then of course nothing could be done. But since there is a constant term, I could take a part of this and add here so that negative coefficients disappear.
So that means we are taking out DC value which is greater than the minimum.
No, it is not RC. It is not RL either, and therefore those considerations do not apply here. What we can remove, that consideration doesn't apply here, because it is neither pure RC nor pure RL. Alright, so we argue like this, that perhaps what we are missing is, because it cannot be RC, because it cannot be RL, it is not pure LC either, it is RLC. Therefore perhaps what we have to do is, we have, let's say, some constant K0, let's say, or no, let's put it something else. Some constant K1 plus K2 divided by, we found one of the residues positive, so let's make it S plus 1 plus, let's say, some K3 by S plus 4. K3 came out to be negative. Why don't we try K3S by S plus 4? You see what I am trying here?
Yes, sir.
A resistance, a parallel combination of resistance and capacitance, and this will be a parallel combination of resistance and inductance. Now, nobody told me beforehand whether K3 will be positive or not, and there is nothing sacred about assigning the pole at S equal to minus 4 to K3S by S plus 4. I could have done it the other way around. For example, I could have written K1 plus K2S by S plus 1. Let's do this first. Plus K3 by S plus 4. Why don't I do this? Because to find K3, the value of K3 is found by the same procedure. And K3 was found to be negative, so we don't try this. Do you follow this? These are various steps one has to apply. As I said, there is no set pattern. You have to exercise your. You see, if I write it like this, then how do you find K3? You multiply the function by S plus 4 and put S equal to minus 4. That we had already found out to be negative, so we don't try this. Now, if I go by this, then what is K3? S plus 4 Y of S divided by S, alright, at S equal to minus 4. And this comes out to be 1/6. Is that correct? Which is very hopeful, which is very encouraging that it's positive. Therefore, all my three constants K1, K2, K3 are positive.
Instead of doing this procedure,
Yes.
so we might have replaced 1 by say 3s plus 4 by 3s plus 4, and then we have added it to.
Precisely that's what I am doing. You see, taking a part of the constant and adding to the that negative coefficient, negative residue term. That's precisely what I am doing. But I am doing it in a more systematic manner. I argue that one of the parallel combinations perhaps is RL. Which can it be? Obviously the one with a pole at S equal to minus 4. Why obviously? Because otherwise we found K3 to be negative.
So how can we show about K1?
How can you be sure about K1? Why should K1 be there?
No, why should it be positive now?
Oh, there is no guarantee. You have to find out K1. What is K1?
5 by 6. 1 minus 1 by 6.
So K1 is now wait a second. There must be a systematic procedure. S plus 2, S plus 3 divided by S plus 1, S plus 4. This I had said K1. K2 is the same as in the previous case. How much was it? 2 by 3 divided by S plus 1. Then I find out 1/6 S divided by S plus 4. So what is K1 and how do you find it? Put S equal to? I could put S equal to 0 also.
No, sir. Dividing by S and putting S equal to 1. Ys by S.
Oh dear. Look, it's not that difficult. See, K1, if I put S equal to infinity, Vikram, you prefer that? Alright, we'll do that. If I put s equal to infinity, this goes to infinity, so I get 1/6. K1 plus 1/6 must be the infinite frequency value, that means it will be 1. And therefore K1 is 5/6. I could put s equal to 0 also. If I put s equal to 0, then I get K1 plus 2/3 equal to 3 into 2, 6 divided by 4. It would give the same result. So my final network is 5/6 resistance, then an RC. Don't you see the 5/6, that 1/6 is now added to that negative residue term.
6/5 resistance. Because it's admittance.
Oh, this is admittance, yes. 6/5. So it is not this structure at all. It is a Foster 2 type structure. So I have 6/5 resistance, then can you give me the values? 1 RC. Can you give me the values?
3/2 is L.
3/2 is L. Okay, so I have R and L. Why is 3/2 and L? This is admittance.
Yes, sir.
Okay, you are right. 3/2 is the inductance and the resistance is
3/2.
3/2. What about the capacitance? Capacitance is 1/24 and the resistance is 6. That is a correct structure. Is there an alternative? Can you find an alternative? Another structure? Foster type? Why not? Take the impedance. Take the impedance as G of S equal to S plus 1, S plus 4 divided by S plus 2, S plus 3, and expand like this, sum K1 plus K2 by S plus 2 plus K3 by S plus 3. Will this work? Will this work? And why not? What is? Why should K2 be negative? The reason is obvious. You have to see.
Terms are estimated to distribute.
You see, if you assume this form, obviously you are assuming an RC network. This is not an RC function, and therefore one of the residues must be negative. Which one is negative? You once said K2 is negative. If K2 is negative, then you assume this to be of the form K1 prime plus K2 prime S divided by S plus 2 plus K3 by S plus 3. All right. You don't find K1 to start with. You find K3 in the usual manner. You find K2 prime by multiplying by S plus 2 and dividing by S and putting S equal to minus 2. Then you put either S equal to 0 or S equal to infinity to find K1 prime. Is the point clear? So the structure that you will get is the Foster 1, in which one parallel circuit is RC, the other parallel circuit is RL. Agreed? Now let us see. Is there any question? As I said, this has to be trial and error, but a bit of common sense has to be applied. Then you can avoid some unnecessary wastage of time and efforts. Now let us try continued fraction. Our function is s squared plus 5s plus 4 divided by s squared plus 5s plus 6. All right. This is my impedance function, and blindly let us start continued fraction expansion with highest powers. You will get negative, so this doesn't work. What about starting with the lowest powers? Let us say y of s 6 plus 5s plus 6, 4 plus 5s, oh, s squared. S squared, 4 plus 5s plus s squared. Let us see if this works. 2/3. Oh no, 3/2 or 2/3? Okay, 4 plus 10 by 3s plus 2 by 3s squared. I am left with 5 by 3s plus 1 by 3s squared, 6 plus 5s plus s squared. The quotient is 18 by 5s. Okay, good enough. This is y, this is z. So I get 6 plus 18 by 15. Is that right? Okay. Which one is 6 by 5s? This is okay. Oh, 6 by 5. All right. All right. So I get 25 minus 6, 19 by 5s plus s squared, 5 by 3s plus 1/3 s squared. Now what? Where is the first one? Because we started the. Oh no, we didn't invert it. This is z. Thank you for the correction. This is y. How much is this? 25 by 57. So 5 by 3s plus. I did not go further because the remainder is negative. Okay, so sorry about it. This doesn't work. And you can try taking y.
Expand the lowest power, starting at lowest power. Can we expand the impedance or admittance? Or we can do either?
Oh, depends on what did you start with. You see in here my z of s was this, and I started with lowest power 6 plus 5s plus s squared in the denominator. Therefore, the quotient is impedance. Now, there comes now a trick or exercising some ingenuity or trial and error. Yeah. This one, we did try this, isn't it? Did we try?
Yes.
We did. It didn't work. What happened to my? Well, it didn't work. Same page? On the top, yes. We did try. You see, obviously the remainder will be negative. Now, what we ask is the following. It is at this stage that the continued fraction expansion falls to ground. Suppose at this stage we reverse the order. In other words, we come up to this,
Take the highest degree.
then I do continued fraction expansion starting with highest powers. Let us do that. S squared plus 19 by 5s divide 1/3 s squared plus 5 by 3s. As I said, there is no set procedure. The first quotient is 1/3 s squared plus 19 by 15s.
No, sir, 5 by
19 by 15s. This is okay. So I get 15, 6 by 15. That's right. 30. Now, how did you get 6? 3 times 5, 15. Okay. 6 by 15s. Then s squared plus 19. 2 by 5s. All right. Then I get 5 by 2s. 5 by 2s s squared. 5 by 2 is okay. All right. Then I get 19 by 5s. 2 by 5s. It does work. All right. I don't have to proceed further. I know it works. All right. So it is not necessary that you continued fraction expansion Now, why did we decide that we will do it at this stage? At this stage? Because the next stage was coming negative. So we do something to the previous stage to correct it. If it did not work, then what would we have done? We have said sorry about it, we can't do it.
1 by 3 is
Because the other way around it didn't work, starting with the highest
So
power.
what are the values of impedances and inductances? So the dimensions.
Oh, dimensions are okay.
So in the next
Dimensions are okay. Starting with highest power or lowest power that does not change the dimension. No. Dimensions are okay. There may be other variations inside if it doesn't work. For example, if you take the reciprocal and then start with highest power or lowest power, then the dimension would have changed. Okay?
Is it okay that we reverse this at this stage?
We can.
So then we change the dimension as well.
Then we change the dimension. The next one would not be an impedance, then it would be an admittance.
Yes, sir. Like we start dividing 19 by 5s by s square.
By this quantity.
This one.
Yeah. This is also possible. That is, at some certain stage, you can either go from lowest to highest or highest to lowest, or you can take the reciprocal and go. But as I said, purely trial and error. There is nothing that ensures that there exists a continued fraction.
So might it have turned out positive, negative, then we would have changed the terms again, powers again.
That's right. We will try that again.
Before possible.
Then in this case, 1 by 3 is better.
There are many possibilities. Many possibilities.
So even if the quotient is coming out of the positive,
Yeah.
still we can take the reciprocal or change the
Still we can change the reciprocal if it works. You see, why were we encouraged to try reversing the order? There must be a reason. Why were we encouraged to try this procedure out? That instead of
coefficient of s square came out to be negative. So if we reverse it,
no, that is a mechanical thing. We tried reversing, but why didn't we give up at this stage?
different circuit.
We had a hope that because one circuit has been found out, one possible circuit has been found out, we know that there exists an indefinite number of circuits. And therefore, there is no reason why partial fraction worked with a slight twist, why continued fraction would not work with another slight twist. Okay?
Excuse me, sir.
Yes.
Sir, then once we get negative, we turn into the other power.
Correct.
So between the highest power factors. Highest power terms.
What is the other part? What do you mean by other part?
So initially we started with removing the lowest terms.
Correct.
When we get negative term, from there we shift to removing highest power terms.
We can start with either highest power or we can take the reciprocal.
So if again we get a negative term, can we shift to the lowest and start removing the lowest?
Yes, why not? Anything is permissible so long as you don't change the dimensions, so long as you don't change the numbers.
So we can keep changing after every step.
You can change, you can keep changing after every step. It will be a mixture of cover 1, cover 2 and yes.
You said that you will be taking the reciprocal, that means changing the divisor and divisor.
Right. So instead of the quotient being an impedance, it will again be an admittance. Okay, so two admittances will come in parallel or two impedances will come in series.
So then how do we make the circuit?
Oh, it will not be a... Oh, how do you make the circuit? At that stage, the two quotients, if they are the same dimension, then they will come either in parallel or in series. They will not come as one in parallel and the next one is series. That will not happen. Yes, that is the question.
Can you tell the relation of this one, sir?
Pardon me?
Can you tell the circuit relation of this one?
Oh, circuit realization. Okay. Let me complete it then. Oh, tell me what this 2 by 19, so 2 by 5s, this is 0. Now, if we come back, this is a z, so this is a y.
No, sir, that was 1 by z is also z. So because we...
What is a z? Hold it. Oh, this is not there.
Isn't the first
This is a z.
See, isn't the first term of y, sir? Because the given function is y.
No. We took a z. We started with z. 6 plus 5s plus s squared divides 4 plus 5s plus s squared. So it's a z. Z, y. This is z. This is y. This is z. So, my circuit would be this. 2/3, then what would this be? Inductors,
Inductor 5 by 18.
5/18. The next one,
25 by 57.
no. Before that there is a resistance of 1/3.
1/3.
Next one is a capacitor 5/2. That was the effect of reversing the order. The next one is a resistance 2/19, and then the remainder is 0. Impedance 0 means a short circuit. So this is the total circuit. Okay, since a serious consideration of one port synthesis RLC is beyond the scope of this particular course, we now turn attention to a glimpse into a transfer function synthesis. And we recall a few facts. As you shall see, by definition a transfer function is a network function that relates the output at one port to the input at some other port. That is the definition of transfer function, right? Otherwise, if the port is the same, the cause and effect are the same at the same port, then you call it a driving point function. A transfer function therefore relates the effect or the response at one port to the cause or the excitation at some other port. And you have already seen an example generator here. A current generator I1, and we measure the voltage here V2. Then what is V2 by I1? It's a transfer impedance, okay? And how is it related to the parameters of this circuit? And which parameter? Z12 or Z21? Z21, okay? This is described by the Z matrix. This is Z21. All right. Of course, I know that if this is a reciprocal network which we have been discussing, then this will also be equal to Z12. Now, suppose we take this network with a source impedance, with a voltage source, and we keep this open and measure the voltage. Then V2 by V1 is the open circuit voltage transfer function, and this is expressed in terms of Z21 and Z11. Z21 by Z11. It's very simple. Write V1 equal to I1 Z11 plus I2 Z12, and V2 equal to I1 Z21 plus I2 Z22, but I2 is 0. Therefore, the ratio simply becomes Z21 by Z11. I can also express this in terms of Y parameters. And if you don't recall, this is Y21 by Y22 with a negative sign, and it comes because I2 equal to V1 Y21 plus V2 Y22, and I2 is 0. That's how it comes. These derivations, I mean, how you get this, you should be able to remember, okay? Simple things like this. Now we complicate matters a little bit. Suppose we have a network N, passive reciprocal network N, driven by a voltage source V1 and terminated in a resistance R. The current is I2, and what we are interested in is V2 by, let's say, I1. This may be a current source. Well, let's put it as a source. It may be a current source, it may be a voltage source. Suppose we want V2 by I1. You recall we had used a symbol for this. This is a transfer function, but not the Z parameter of the network N, because N is being augmented by capital R. We call this a transfer impedance, and we used a capital Z for this. Z21, that is the response point to the excitation point, and this is simply equal to Z21R divided by Z22 plus R. Do you recall how this is done? How this is derived? How? Z21?
So the previous one.
No, this is capital Z21.
That before I2 equal to 0.
No, capital Z21 is the transfer impedance of the terminated network. There is a small Z21 here which relates to N.
No, sir, should that V2 by I1 is equal to capital Z21 for the condition that I2 is equal to 0?
No, 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 no. This is the actual condition. Terminated, under terminated condition. Okay? How did you obtain this? Give me a simple method. V2 equal to minus I2R and
So V2 is equal to I1 Z21 plus I2 Z22.
I1 Z21 plus I2 Z22. That's wonderful. Absolutely wonderful. If you go back to the basics, there is no, you cannot make a mistake. Well, there is a simpler method. If you don't want to write the equation, you look at the Thevenin equivalent and drive by a current source. What will be the open circuit voltage? I1 Z21 and the output impedance would be Z22 because current source, and there will be a division between Z22 and R. That's it. Is the point clear? Not clear. This would be I1 Z21. This will be the open circuit voltage. Then the Thevenin impedance would be Z22 and you have an R. This is V2. Okay. So there are simple ways. I have done this in detail. I am simply reviewing them, but it is necessary that you recall at least the simplest of them. We also treated the most general case, that is, we have a VG generator in series with a resistance R, a network N and a termination of R 2, V2. We have found out that V2 by V1 is equal to Z21 R2 divided by Z11 plus R1, this is the effective Z11 of this network, multiplied by Z22 plus R2, effective Z22, minus Z12 Z21. Of course, if you remember this, then you can derive every other case as a special case of this. Isn't that right? This is the most general case, terminated at both the ports. And at one port is the excitation, at the other port is the response. The point to notice from all these simple examples is that the transfer function, yes? V2 by VG. V1 is here. Thank you for the correction. I was wondering why people have not noticed this. Is there any other mistake? All right. Silence says that you have not been able to detect, which means in all probability there is no other mistake. Okay. The thing that I want you to notice is that in computing these transfer functions, simple transfer functions, we have always stuck to Z and Y parameters. And this is one of the philosophies of synthesis. Z and Y parameters came first into the picture. Scattering came much later. And the H parameters came. H parameters gained their prominence when transistor was brought into the field of electrical engineering. So let's say around 1949 or 1950, the H parameters gained their prominence. The transmission parameters gained prominence when people wanted to build systems as a cascade. Okay, but basic transfer functions we work only in terms of Z and Y parameters due to historical reasons. The other reason is that it is more convenient to use because impedance and admittance, we know the properties. You see, all these transfer functions involve Z12 which is equal to Z21 and then these driving point functions Z11, Z22. We already know the properties of this. Okay, at least two element kind we know completely, one element kind we know that they have to be positive real. Either this or you can express in terms of Y parameters, that is minus Y12 and minus Y21, then Y11 and Y22. We also know the properties of driving point admittances, that must also be positive real. So if we now investigate the properties of this transfer impedance and this transfer admittance, that is y21 and z21, if we know the properties of this, then we should be able to know the properties of a transfer function, properties of a two port. All right. So we shall now spend some time on the properties of this transfer impedance and this transfer admittance. Okay. But before that, some general observations. You see, whatever the transfer function is, some general observations. Let us call the transfer function as capital T of S. The transfer function could have the dimension of an impedance, could have the dimension of admittance, or could be a dimensionless transfer function. If it is dimensionless, then it could be a voltage ratio or a current ratio. But whatever it is, if S is real, what can you say about T of S? It must also be real. Why? Because T of S contains Z12, Z21, Z11 and Z22. Z11 and Z22 we know they are real for S real. What about Z12, Z21 or Y21, Y12? They must also be real. They are also rational functions, and there is no reason why they should not be real for S real. So if S is real, T of S is real. This should be if you get a transfer function having a complex coefficient, you say sorry, we cannot realize this. Second property, irrespective of what the transfer function is, can you have a pole in the right half plane? No. No poles in right half plane, because we are talking of passive networks. Passive networks are always stable. All right. And therefore, there cannot be any poles in right half plane. If there are poles on the j omega axis, can we have multiple poles on the j omega axis? No. No multiple poles on the j omega axis. And what is the logic now? Because this leads to instability. That is, even if the input is bounded, the output shall not be bounded. Give an example. Suppose we have two pairs of poles at plus minus j omega naught. Then the time domain response shall be of the form t times sine omega naught t or cosine omega naught t. And obviously, as t goes to infinity, these oscillation amplitudes grow indefinitely. So no multiple poles on the j omega axis. This must be shared by all transfer functions. If there is a multiple pole, then you give up. You don't proceed further. Next one is a tricky question. Suppose T of S is written as P of S by Q of S. What can be the maximum difference in degree between the two? Well, I said it's a tricky question. So maximum difference obviously can be only 1. Isn't that right? Because if the difference is 2, we shall have a multiple pole at infinity, which is a point on the j omega axis. If Q of S, I think I have said what I wanted to say. There is the maximum difference cannot exceed 1. But can they be equal? Yes, it can be equal. No, I have made a wrong statement. I take back. Maximum difference in degree can be more than 1. Let me tell you. What I should have said is that degree of P, the numerator degree, cannot exceed denominator degree by more than 1. This is the correct statement, because Q of S degree can be 3 and P of S degree can be 0. For example, you take this network, you know that this is Can you write down its transfer function by inspection, by just looking at it? That is, I have a voltage source, and this is the voltage that is my concern, V2 by V1. What would be the form of this? Pardon me? 1 by S square plus, let's say, B1S plus, yes, what should be this coefficient? Constant B0. Is there a restriction on B0? Oh, it must be positive. But don't we know its value? I appeal to your common sense. What is the DC transfer function? If you apply DC here, of course it is a constant. But what is the value of the constant? 1, it has to be 1, because at DC this is open, and therefore whatever voltage you apply here will come here. No current is flowing. Therefore B0 has to be 1. And you see that the numerator degree is 0, the denominator degree is 2. They are differing by 2. They can differ by any number, in fact. But the restriction is that the numerator degree cannot exceed the denominator degree by more than 1. And the reason is that if it exceeds by more than 1, we shall have a multiple pole at infinity. Here what is wrong, what is right here and what is wrong here? There is a multiple 0 at infinity, that is permitted for a transfer function. It is not permitted for a driving point function. Why not? Why is such a thing not permitted in a driving point function? Because the reciprocal of a driving point function is also a driving point function. And if there is a multiple 0 at infinity, there shall be a multiple pole at infinity of another driving point function, which therefore ceases to qualify as a driving point function. The reciprocal of a transfer function is not necessarily a transfer function. For example, the reciprocal of this cannot be realized. Why not? Because it has a multiple pole at infinity. Is the point clear? So this is the first difference between a driving point function and a transfer function. That if a transfer function is written as P by Q, the degree of P can be at the most 1 greater than the degree of Q. But the degree of Q can be any number greater than the degree of P, any number. Depends on the complexity of the transfer function. Just one more observation, obvious property, then then we will see, we will call it a class. Suppose T of S is written as M1 plus N1 divided by M2 plus N2. We have always been doing this with driving point function. Now I appeal to your common sense and ask you, what is T j omega squared? In terms of M1 of j omega and N1 of j omega. M1 of j omega square, agreed? Then plus N1 of j omega square divided by M2. I set you a trap and you have fallen into it. No, I am finding the magnitude squared. Magnitude squared should be real part squared plus imaginary.
Must be able to change it into the denominator into real part.
Any other brilliant suggestion? Huh?
Only the real part of
it won't be M2 j omega.
Say it again.
It won't be M2 j omega.
It won't be M2 j omega.
Just omega. So it's not a function of j omega.
All right, we put S squared equal to minus omega squared. Okay, that is not the inaccuracy. There is something else grossly wrong, and I have cautioned against it several times. You see, N1 is the odd part. Suppose N1 is equal to S, then what is N1 of j omega? It is j omega. Would you bring here N1 squared j omega?
Mod of N1.
That's it, that correction is needed. You see, the imaginary part is n1 j omega divided by j. Yeah.
But we are taking the magnitude. So
That's
it will
right.
be m1 omega square plus omega square. So
Uh-uh.
we take from,
Just a minute, just
so
a minute.
suppose m1 is equal to s square.
We take a function, let's say s squared plus s plus 1.
Yes, sir.
Then 1 minus omega squared is the real part and plus j omega. So the magnitude squared would be 1 minus omega squared whole squared
Plus omega square.
plus omega squared.
So that
If I insist on taking this, I must add a negative sign, minus j omega whole square. Isn't that right? Please be careful about this. I have cautioned you again and again that when you take the odd part and put s equal to j omega, then the imaginary part is that quantity divided by j, because j comes into the picture.
also we can have plus mod of n1 j omega also.
You can do that. You can take the mod. Okay. Now the question that I was asking is,
So again, that means so m1 square minus n1 square is saying.
yeah,
Will that be?
that is correct. Well, it should have been clear also from the consideration, very simple consideration. I was hoodwinking. I was trying to take a detour and confuse you, and you have been confused. Please, please come out of it. You see, what you have to do is to find out the magnitude squared, take m1 plus n1, and then you take m1 minus n1 j omega. This is the numerator p j omega, and this is p minus j omega, which will make the numerator magnitude squared. So t j omega squared, magnitude squared, is equal to the numerator squared divided by the denominator squared.
We do the same negative sign. I was, you didn't replace the negative sign in the denominator.
No, but if I multiply the two, isn't it m1 squared minus n1
No,
squared?
sir, this is okay
Also
in
in
the
the
numerator. In the
Oh, you'll have to do that also. Yeah, we'll have to do that also. The question that I am asking now is, I have discussed this earlier. What can you say about this magnitude squared function? It must be purely even. Isn't that right?
Yes, sir.
Magnitude squared function cannot be negative.
Yes, sir.
It only contains even powers of omega in the numerator as well as in the denominator. What about the magnitude? That is the square root of this. Magnitude, that must also be an even function. And what about the argument, angle of t j omega? Must be an odd function. Okay? This we have said again and again, and you will see the reflection of this evenness and oddness in the synthesis procedure. They play a dominant part. We will continue this next time.